The first part of question 4 wants us to construct an equation for oxidation of V2 plus to VO2 plus using manganate 7. With redox equations, what you always should think of doing, whether it tells you to or not, is to construct the two half equations first and then add them together, because in all but the simplest cases that is the safest and ultimately often the quickest way of making sure you get it right. So what we do first is turn that into a proper half equation, and then we add them together. And if you just learn that as what you do and don't waste time agonizing about is that the best way, then you get these questions done quickly and efficiently. So the method for constructing half equations is just a sort of simple 4-step process, and you just have to learn it and do it, and it's quick and easy then. So first you balance the elements which aren't hydrogen and oxygen, which they are already, one vanadium on each side. Then you balance the oxygens by putting waters in. So you need 2H2O, so that you then have 2 oxygens on each side. Then you balance the hydrogens by putting H plus in. And at the moment we've got 4 hydrogens on the left, none on the right, so we need 4H plus here. And finally you balance the charges by putting electrons in, because this is a half equation. And at the moment we've got 4 plus 1 is 5 plus on the right, but only 2 plus on the left. So it's 2 positive over here, so we need 3 electrons. That's the half equation. And then we've got to combine that with the manganate 7 one, which it already gave us, so that one is in the question. MnO4 minus plus 8H plus 5E minus goes to Mn2 plus 4 waters. Now in order to combine them, they have to have the same number of electrons. One on the right, one on the left, so that when we add them up, those electrons will cancel out. So that's the next job, is to modify the equations so they do. And 3 and 5, their lowest common multiple is 15. So what you do is say, right, let's engineer these so they each have 15 electrons. So we multiply the top one by 5 VO2 plus 10H2O. It's multiplying every term by 5. So you get big numbers, but it doesn't matter. It's an easy process, just multiplying through by 5. So we get that. And then the bottom one multiplied by 3, so that we get 15 electrons. So 3 manganates, 3H 24H plus 15 electrons will give us 3 Mn2 plus and 12 waters. And now we can add those up. So just put everything from the 2 left-hand sides here, 5V2 plus 10H2O plus 3 MnO4 minus plus 24H plus. I won't write the electrons down because we know those have cancelled out. Gives you 5 VO2 plus 20H plus 3 Mn2 plus 12H2O. But you can't leave it like that, because it's got waters on both sides and it's got H plus on both sides. And if ever you have an equation that has the same thing on both sides, it's wrong. So it's got to just become a reflex to make sure that isn't the case. So with these half equation things, once you've added together, you should immediately then look for what needs cancelling. And you can see there's a lot, because you've got 10 waters here and 12 there. So we can cancel 10 from each side. So that disappears completely, and that goes down to 2. And we've got 24H pluses going down to 20, so that goes down to 4H pluses, and we lose that completely. Nothing else cancels, so now we can add those together. Just write down the cleaned up equation. So 5V2 plus 3 MnO4 minus plus 4H plus 5 VO2 plus 3 Mn2 plus 2 H2O. And that should be the right answer, but always check before you move on. Make sure that the charge is balanced. It's a quick way to make sure it's probably right. So you've got 5 2s are 10 plus 4 is 14 plus, and 3 minus is 11 plus on the left. And then you've got 5 plus and 6 plus adds up to 11 plus on the right. So that gives you confidence that that's the right answer. In the second part of the question, it gives us the equation for a different reaction of manganate, this time with Fe2 plus to produce Fe3 plus. And it tells us that we've got Fe2 plus in the form of this hydrated salt, FeSO4.xH2O, where X is this unknown amount of water. We've got 15.23 grams of that in 500 cm cubed of water. From this 500, we take a 25 cm cubed sample and titrate it with the manganate, and we require 27.4 cm cubed of 0.02 molar manganate. So from that we can derive X. Now in this question it made it reasonably straightforward because it led you through it a step at a time. In an A-level question it typically doesn't do that. It typically will just give you that information and then leave you a blank space. So you have to learn what the steps are so that you will be able to get through it efficiently and correctly. So the starting point is to get the moles of manganate, and that's what you always do in a titration. If you know the concentration of one of the solutions, your starting point is to work out the moles of that one. So you get the moles of MnO4 minus is concentration times volume in dm cubed. So if it's a titration calculation, you shouldn't really be floundering around wondering where to start, because you know that's what the opening gambit is going to be. So concentration is 0.02, and the volume is 27.4 cm cubed, but we have to divide that by 1,000, so that's 0.0274, and that gives us 5.48 times 10 to the minus 4 moles. Now we look at the equation and say, if we know the moles of manganate, we can get the moles of Fe2 plus, because this is what we're interested in, and you can see it's 5 times as many. There are 5 of these for every one of those, so we've just got to multiply by 5 to get the moles of MnO4 minus in the titration, so the moles of Fe2 plus in the titration. That's in the 25.0 cm cubed sample, is 5 times the moles of MnO4 minus. So we just have to multiply that number by 5, and that equals 2.74 times 10 to the minus 3 moles. So the next thing is to be clear that that's the number of moles of Fe2 plus in 25 cm cubed of solution. But we made up a total of 500 cm cubed of that solution, and what we need to know next is how much there was in that total volume. So we have to scale up, and in most titration questions you should be looking for the scaling up step. So that's the next step, which is to get the total moles of Fe2 plus in 500 cm cubed. And to scale up, we're just going to say, right, to get from the moles in 25 to the moles in 500, we've got to multiply by a factor of 500 over 25. So it's the total volume divided by the sample volume times 2.74 times 10 to the minus 3. Okay, so we're multiplying by 20, and that gives us 0.0548 moles. So that's the total moles of Fe2 plus in the 500 cm cubed of solution. But that Fe2 plus came from this compound. And you can see from the formula of that each mole of FeSO4.xH2O contains a mole of Fe2 plus. And therefore the moles of Fe2 plus, which we just calculated, equals the moles of FeSO4.xH2O. Okay, so just to be clear, what the titration has measured is the moles of Fe2 plus, but because the Fe2 plus comes from this compound, and each mole of the compound contains a mole of Fe2 plus, this number of moles is also therefore equal to the moles of that compound. And that leads us into the next step, which is that we can now work out the MR of FeSO4.xH2O, because we know the mass and we know the moles, so we can just calculate that. The mass was 15.23 grams and the moles is 0.0548, and that is equal to 277.9. So now we have the MR of the whole compound, including the water of crystallization. So this whole thing adds up to 277.9, but we can work out what the FeSO4 contributes to that by just adding up the atomic masses of FeSO4, which comes to 151.9, and therefore the XH2O is the difference between those numbers. So we then get that the MR of XH2O is equal to 277.9 minus 151.9, which is 126.0. And of course, each H2O has an MR of 18.0. So if X of them adds up to 126, we therefore get that X is equal to 126.0 divided by 18.0, which is 7. And it works out to exactly 7 in this case. Sometimes it won't, it might come to 6.9 something, but we're looking for whole numbers, so you would round there. So that's our answer. In other words, the compound that we started with was FeSO4.7H2O, was the hydrated iron 2 sulfate.